Today on Archive Dives with Oxen.ai, we'll be diving into efficient streaming language models with attention sinks. This is a really interesting paper that has a lot of observations about the attention mechanism within a transformer itself. They add what are called attention sinks to existing transformers, as well as pre-train a transformer with an attention sink during the pre-training process. They show that this allows your model to have stable language modeling up to sequence lengths of 4 million and beyond in theory. What this doesn't allow is for that 4 million length sequence to remember everything or be able to refer back to the start of the sequence. It's just purely this stable language generation up to 4 million tokens. And we talk about why that's interesting and what a attention sync is and what a streaming LLM is in general. Today's our first guest host for Archive Dives. We have Daniel Veroli from Zapata AI. He's super brilliant, answers all the questions to the T. Every Friday we get together with a group, and this was the first time that we had somebody from the meetup suggest or offer to host an archive dive and do the research themselves. So if you're interested in doing something similar, Daniel set the bar high, but feel free to reach out to us on the Discord. We're happy to share the love of the presentations, and I'm sitting by his side in the chat monitoring for questions and asking some questions that I had of my own. So with that said, we'll let Daniel take it away. Well, welcome everybody to Archive Dives with Oxen.ai, and our guest host today is Daniel Veroli from Zapata AI. Daniel, I'll let you take it from here.
Thank you. Yeah, so as Greg had mentioned, the focus of today is going to be the paper on efficient streaming language models with attention sinks. Really cool paper. Very interesting results, and just overall, I thought very well put together. So hopefully everyone enjoys it and finds it useful. I was thinking about how to actually start this because I think this paper leans heavily on kind of application and more applied ML. And so I thought it's extra important to motivate what's going on and kind of just so you can appreciate the final results and the solution to it. So I think as a result, what I decided to do is to start with a bit of a kind of setting the stage and doing maybe a little bit of recap, because there's some parts here that maybe not everyone is familiar with, but they are important for the paper. So with that said, let's sort of get into some things that kind of just, so start from the beginning essentially. And so when you train a transformer, right, which is the underlying architecture for your LLM, likely, you have some kind of context window that you set at training. It's not a hard stop. The model can, in theory, process more tokens, but that's kind of what it's trained to work with. And this can vary by model, right? This usually does vary by model. So a few examples here. So, gives you a rough idea of the range. And so once you have that LLM trained with its context window, which is going to be important in a bit, you probably want to use it for something. And for example, you might want to deploy it in production in one setting or another. And to do that, you have to make a few considerations. And so you might be familiar with some of those considerations, right? But if you're talking about production setting, it's going to be very important about how fast you're generating new tokens. So inference latency is a big deal. GPU, how much GPU memory you need is also a big deal, right? GPU memory is expensive. And you need to be able to fit your LLM plus all the inputs, outputs, and a bunch of other stuff. If you can't do that, you can't really run your application. And of course, the quality of outputs, right? So if you have the fastest model in the world and you have just infinite GPU memory for whatever reason, lucky you, but it's not going to be any good if you can't generate good outputs. So, okay, so we established those considerations. Probably nothing too surprising yet. But what if I told you that, and maybe this is also isn't too surprising, but your training context window can actually have an impact on all three. Great, right? So what do I mean by that? Well, I think it's fairly reasonable to say, okay, so longer inputs can mean like longer inference time, right? So That's one way that your context window can input, right? So depending on how long that is, that can take longer. Longer inputs can also mean you need more GPU memory. If you have a 10,000 sized context window and you're feeding sequences that are 10,000 tokens long, that's going to be, you need more memory for that. And longer inputs can actually affect your model perplexity. And so this is where the context window kind of comes in from another angle that may be a little bit surprising. And we'll get into this in a moment. So with that kind of set, right, let's kind of focus more what an example, like what you might be doing, and keep those things in mind. But let's pretend you're building a chatbot, right? That's a common application with LLMs today. You see it fairly often, and some are more useful than others, and some are really, really cool. So I think it's a very reasonable application to try and explore. And it's one that the paper talks about as well, so that's great. So let's take an iterated approach, and again, we're doing this to motivate like what the problem is and what the paper is offering. Now, keep in mind this is a hypothetical, so it might not be 100% accurate, but again, this is more to motivate the paper and the results. So you pick some model, it could be Llama 2, 77 billion, for example, and you're not really doing anything to the model, right? So nothing fancy, just the model really as is. And you have some users who start using your chatbot. And what can happen is when you observe is that, number one, it can sort of starts getting slower as your conversation gets longer. And the other thing that might happen, or that you might observe, is that at some point just things crash. That's one option, right? Or the other option is they don't crash, but as your inputs get long enough, your model starts generating gibberish, and that's not good as well. So your user complains, the user doesn't use your app anymore, and well, so you're sad. So you need to fix that. So you go back and you do a second iteration, and maybe do some reading and so on. And this is slightly there we go. You do some reading and you say, all right, if it's crashing, I don't want it to crash. So I want to keep things under the context window. And maybe you go out and you read and you say, oh, okay, it seems like as I start to go beyond the context window, right, even though the model can in theory handle it and maybe not crash, well, it's starting to, that can affect what it's actually going to be generating and the quality of those outputs. So you say, all right, I'm just going to chop off anything that doesn't fit in, right? Just keep whatever latest text that fits in and get rid of everything else. And great, your model doesn't crash, or maybe it's it's generating reasonable results, things as you would expect, but it's still kind of slow. So all right, you go back and maybe you post on Reddit and you ask people, okay, how can I make my LLM be faster? And they tell you, all right, well, there's this thing called sorry, this should be third iteration, right? Let's see if I can copy this. There we go. Whatever. So you go to Reddit, you ask, what can you do? People tell you about KV caching, and this is a whole topic that can be probably a whole session of its own. But basically, right, when you generate a new token, every token that came before is going to remain the same. So there's going to be a lot of computations that you're going to be redoing. So instead of redoing those computations, you just store the results of those computations in this KV cache, specifically KV because of the keys and values in the transformer. And when you need to predict the next token, you reuse what you computed before. And this kind of gives you a substantial inference boost, right? This comes at a trade-off that you need memory to store all this, right? So that's also important to note. And we don't need this twice. I think once is sufficient. But so you're like, all right, cool. KV caching to speed things up. Great. I'm going to add that. You go ahead, you add that. And yeah, your LLM is now faster. And you just decide that, all right, I'm just going to keep putting stuff in the cache, right? I'm just going to keep throwing things in. And as I mentioned, right, the cache needs memory. So now you're in a situation where your memory usage just keeps growing and growing. And let's pretend you have some kind of autoscaler that just keeps giving you more and more GPUs infinitely. And so now you're bankrupt. So not good, right? You don't want that. But surprisingly, your model is still actually generating weird things. So not great. You're broke and your model is generating weird things. So just all around not good. And kind of a little bit to just prove that this isn't all hypothetical, right? There's a link to this blog post, but someone has done experiments and they've shown that this is kind of what you observe, right? You get this linear increase in memory, the dashed line, and or memory usage, and the perplexity, which is your measure of how good the tokens that your model is predicting are, is also beginning to shoot up. And note this is log perplexity, right? So this is quite a spike. So with that happening, you decide, you know what? I'm going to take a step back and I'm going to think about what to do. And I'm going to think about what I actually want. So you do that and you decide that, all right, I could have the best model in the world. I could have AGI at my fingertips, but if it's taking a second per token, you know, am I even okay with this, right? Is this really what I want? So the inference needs to be fast, or as fast as you can really get it. And it needs to keep going, right? For the purposes of you're in this streaming context, right? You want the chatbot to just keep going and going and going. And you don't want it to, run out of memory. You don't want it to start generating gibberish when the conversation gets longer than the context window. And basically you want it to just, continue into infinity, right? So, if the user has 3 days worth of conversation and picks up again on day 4, you want it to keep going. So we've discussed this, right? Set the stage. I don't want to use the word context because there's already enough context here, but it's the transformer related context. So with that in mind, right, with all this that we tried to fix our issue, we're going to slowly start drifting into the paper. Hopefully this kind of setting the stage helps a little bit.
Daniel, as we're diving in, can you, when we get to the key KV cache part again, can you give a little intuition about how all that works?
Yeah, I can actually do that right now if you want.
Cool.
If that's so.
We had a question of I don't understand how KV caching works after the first transformer block. Wouldn't the resulting calculation be completely different after that? So maybe that gives you a little context of people asking.
Yeah, I have some information prepared here for this because it's a tough. I don't know that I have the best understanding of this, but there's a blog post I'm linking to that I thought had a good explanation and they visualize this. But at a high level, right? So right, as I mentioned, you're generating new tokens, past tokens remain unchanged. And so this is what your computation would normally look like. You have this query matrix here, you have your keys matrix and your value matrix. But when you're generating, let's say token 5, that's really all you care about. You don't really need, like, once you've computed, a result for token 1 and token 2, when you're computing your result for token 5, you don't really care about recomputing these values here. So effectively, you could say, all right, I'm just going to take the very last, like the last generated or the last entry in my queries matrix and do the multiplication with just that single entry. But then where does this come from, right? You still need all of this and you still need all of this. Well, this comes from the cache, right? So you're going to be caching these results. Sorry, you're going to be caching these parts of your keys and value matrix. And at the end, you're going to get the same result for this token 5, for this hypothetical token 5. And that's exactly what you wanted, right? That's what you're looking for.
So it's kind of like, can we think of it as a dynamic programming technique?
I guess.
So you don't have to recompute everything every time.
Yeah. So you and the reason is I mentioned like why does this stay the same? Well, so once you've computed this, let's say you start generating, you predict your token 2. Token 1 remains the same, right? So those like in an inference setting at the very least, without any dropout or any of these kind of like these non-deterministic layers, you're gonna get the same results. So you're basically just redoing that computation. And so that's what I mean by, you just cache that and then just reuse it later on.
Great.
So kind of from the blog post on next token generation, you're only using the single token, you're only passing in a single token, and the rows from your cached this KV cache kind of get stacked on top of each other eventually. And you build up this cache. And I imagine you're doing this at every layer, right? So of every block within the transformer. As I mentioned, uses extra memory. So with that, let's so with that kind of, and I think that's a great question. And again, I think this is a big topic itself, probably. So there's a lot of information you could explore on it. So, but I think getting a general idea is probably very helpful. So let's talk about what this paper is, right? And what this paper is also not. And within the paper, so we established that the KV cache is needed to improve inference latency at the trade-off of using memory. And the existing strategies to actually manage this cache have certain limitations, which can be anything from like loss of model performance, higher latency, and or GPU memory requirements. It could be one, it could be multiple of these. So what the authors are proposing here is really a modification that enables LLMs to work in a streaming context. In other words, where you have this like scaling to an infinite amount of tokens, while maintaining perplexity, which is performance, right? Kind of all the way into your hypothetical infinite number of tokens. Maintaining a finite memory footprint, and then also having good latency. And I say good because I think it could still be, it's not necessarily going to be super fast, but we're talking about a relative, faster than other approaches. And what this paper, so what's important to note here is what this paper is not, because this only hit me about like halfway into the paper, what this is actually not doing, which I didn't realize. But this isn't extending the context window, right? So the context window remains fixed. And what this means is that if you have millions of tokens, even if you can keep going, you can't recall information that's like 2 million tokens back, right? So you can't go beyond the context window as far as extracting information. And so what this means is that by itself, this approach doesn't really give you much in terms of long-term document QA or summarization. It's really great for tasks where you need short-term memory. And this can be some types of chatbots, and it can be short-term QA, right? So I think this is really important to note because, again, I think it just helps set expectations as well. But also, I think also helps appreciate what the results here are and kind of why they're important. As a side note, there are works that try to extend the context window, help the model generalize beyond the existing context window. The limitation here is that no matter if you can extend your context window is great, but it's still finite, right? If you have 4,000 and you go to 6,000, that's still a finite number. The whole purpose of this paper is really talking about, okay, how can we scale to a theoretical, infinite number of tokens?
Can you give a little intuition on why you would want to scale if it doesn't remember the things that are farther back?
Yeah, that's a great question, and I think that's a very valid one that I certainly wondered. So if you think about certain chatbot situations, you're asking questions about things that happened recently. The reason you like, let's say you have a conversation, right, and it's going on for like a few days. The whole point here is the reason you want it to keep going is because you don't want to restart the chat, right? And you want your model to continue in this specific setting of being able to kind of have these short these discussions within a short context window. And I think it's important to note that short isn't necessarily short, right? Because finite is probably the better word here, because 32,000 tokens is still a pretty long context window, so it still gives you a lot. So it's more about recent, right, and kind of recent fish. But to answer your question, in certain settings, right, where you only care about things that happened recently, and people are going to be only asking questions about what happened, like what's been in the context recently. You want to be able to keep going, right? So going back to what I said about the few days, you have a few days worth of chat, and in theory, you could just right, you could restart the chat, drop everything you have, right, and keep going. But that's fine when you start up, right? Maybe the initial when you just restart the conversation initially, but as you keep going, and the user keeps typing and like the LM keeps responding, you're going to fill up the context window, but you want to keep going, right? You're still trying to keep going. So then you either need to recompute the entire cache, or you need to start evicting things from the cache, and that's where things get weird, and that's where the model can start generating weird outputs and just do say random stuff. So I think this is a very specific setting, and that it's kind of right. If you picture again a multi-day chat, when I come back to it on day 4, for example, and I start up, it's fine, right? I have like all this information before doesn't really matter. I'm filling up the cache again. I keep going, filling up the cache, because again, I want it to be fast. But then I hit this, I hit the window. What do I do now, right? I can start recomputing, and it's going to be slow, so the performance is going to suffer, or sorry, not performance, but the latency, the user experience. or I start dropping things, and then I get into this place where I'm generating weird tokens. So that's really the motivation, if that
Got
makes
it.
sense.
It's like the startup time and recomputing the whole thing. That's the big bottleneck you want to avoid.
Yeah, yeah. So this is kind of like once you've started, once you're up and running, you want to keep running, right?
Yeah,
It's not really talking about this up and running phase. It's more about you're going, I want to keep going. I don't want to stop. I don't want to lose performance.
got it. Got it.
Um,
Thank you.
yeah. Yeah, great question. I think this, yeah, very important because again, understand what's the whole purpose here. So let's actually get into the paper now. And we sort of started getting into it, but let's really dive into it. And but hopefully this will be very useful to actually understand what's going on. So slightly formalizing the approaches we've discussed before. So there's going to be 3 plus streaming LLM, which is going to be what the paper talks about, or the focus of the paper. Dense attention is really about just keeping this infinite cache in theory. Just always cache, always cache, always cache. This has issues. So important note here is that here T is the kind of the position of the token you're generating, and it's substantially larger than the context window. So if your context window is 4,000, this might be token like 6,000 or 7,000, something like this, right? So this isn't T less than, so this is not within the context window length. This is surpassing it already. And this is important because that's where things start to break down. So number one, and I'm going to focus really on the perplexity in the first one because it fails perplexity, right? So you get massive perplexity, models generating gibberish, and basically no go, right? Does not, like, you can't have gibberish in your whatever setting you're using this. The same is true for the window attention. So this is where you have, I guess this is maybe a bit, I don't know if this is correct. Well, so window attention, I think it kind of comes up in different contexts as well. But in this setting, you basically have like a finite cache where you're storing your pre-computed keys and values. And when the cache, you exceed the size of the cache, you just evict whatever is the oldest entry, just evict and keep going, essentially, keep repopulating the cache. This has the same issue that perplexity is pretty bad. So again, out the window, it doesn't work for us. The next modification is taking a sliding window with recomputation. And what that means is when you fill up the cache, right, again, so still a finite cache, you fill up the cache, but when you need to evict something, you evict the oldest entries, but recompute the entire cache again. And that is fine perplexity-wise, so great, but it has an unfortunate runtime complexity where it's T is always going to be here, but L squared, which is the context window length, is pretty bad. Consider that your context window can be like 4,000, 10,000, right? So not great. But this is really kind of the best as far as, you want good perplexity, but so you're kind of having to eat the cost as far as inference time. Well, maybe not quite. Maybe you don't have to eat it. Maybe you can just use streaming LLM, right? That's what the authors propose, and their solution actually is, good runtime and great perplexity. So it keeps this baseline perplexity as you exceed the context window length. So what do you
And
actually need to do? Oh yeah,
quick
sorry, go ahead.
question. This is really informative in my mind. There's kind of like 2 things we're optimizing. It's the computational complexity and the perplexity. Can you talk just briefly about what perplexity is, just in case people are perplexed about that word?
Yeah, so kind of a rough summary, right, is this is a measure of how well the model is predicting the next token. And perplexity is going to be essentially the taking e to the power of your loss. So the cross entropy loss in the case of language modeling, or causal language modeling. And essentially this is, right, how and maybe people can correct me here, but my understanding of it is essentially how often the model is predicting the right token, essentially, right? So if you have very, very high perplexity, that means the model is just barely, it's struggling to actually predict the correct tokens. And so it's just predicting things all over the place. And
Yeah,
again, because of cross entropy, right, this is connected to information. And so, high, yeah. So sorry, go ahead, Greg, then we can interrupt.
totally. And I even like to think of the perplexity score as how perplexed is the model. So if you have a high
Mhm.
perplexity, it's really perplexed. And if you have a low, it's not. And how you define the right token is just in the pre-training text, you have the inherent labeled data of what the next token is just in the text that you're training on. And so as you're predicting, you get like this list of probabilities out, And we're saying if you always had the highest probability token as the next token, you would have the best perplexity. And if you're slightly off from that, you would have higher perplexity. So it's just based off of the actual training text that you have.
Yeah, thanks for clarifying. Yeah, that's it's an important part. But yeah, so actually that's great. I like how perplexed the model is. It's very easy to remember. So this is really cool, right? Okay, we get these great results, but what is it actually doing, right? That's a big question. And really what's going on here is you're basically just retaining a certain number of tokens in the cache always, right? So you fill the cache up with these initial tokens in yellow, which are called these attention sinks, and we'll see why later. And you keep filling the cache as you would normally. But then once you get to the cache limit, you don't evict these attention sink tokens. You always keep a fixed number of them in the cache, right? You don't touch them. You start evicting tokens that come after them. So in this case, you would evict token 4 and then 5. And otherwise, really, this is functioning kind of very similar to what we discussed before. The important thing here is that you don't need recomputation, right? So you get the benefits of a fixed size cache, right? So kind of talking about the memory constraints and the runtime complexity, but you're not doing any recomputation. Sorry, you're not doing any recomputation, and so you get the benefits of better runtime complexity while still getting to keep this baseline perplexity that which is what you want. And really, how does it perform, right? So let's compare the different approaches quickly. And basically, what you're looking for in these graphs, right? And sorry, it might be a bit small. I don't know if I can. I think the biggest I can make it. But you're basically the pattern that you see here is that with dense attention, which is right, just keeping this infinite cache, once you hit the pre-training length, your perplexity just goes up. Again, this is log perplexity, right? So this is a big spike. Window attention, you see similar results, and again, this gap may not seem that big, the jump, but again, it's log, so this is jumping quite a bit. And when you look at the last two, right, the sliding window recomputation and streaming LLM, you actually don't really see much green, or well, if you try it, you do see green, but the reason is that you're actually recovering much of that performance with streaming LLM, which is great, right? You get the benefits of the runtime, and you still get to keep that very nice perplexity that you want. So your model isn't perplexed. And speaking of that, if we look at some other results, right, comparing the RAM usage and latency, again, the RAM usage is on par, right, because you have this fixed size cache, but the latency for streaming LLM is much better than for sliding window with recomputation. As a side note, why are we just looking at sliding window recomputation here? Well, because perplexity is so bad in the other cases, we're basically just saying, yeah, we're not going to even look at them. Like we don't care about them. They're not good enough for us. And yeah, so you get these huge performance, so this huge latency improvement. Great. So you get all these things that you want. I'm going to jump into explaining why this happens, because I think that's a very interesting part, right? And maybe people are wondering, so great, this works, but why does it work? And why is this, like, what's going on here? This doesn't seem like, it's just something weird is going on, right? So I am going to talk about, and very much how the authors discuss this with like a small addition that I think is very interesting, sorry. So why is this actually happening and why does this work? So the authors begin by looking at where things go wrong. And what they notice is that things go wrong in the case of window attention without recomputation. As soon as you evict your oldest entry in the cache, the first one, you start to see this perplexity spike. And so what they hypothesize is that these initial tokens are actually important for the LLM stability. And I don't know why, there we go. They're important for the LLM stability, or the stability, maintaining that stability of the LLM. Okay, so maybe they're important, right? But why do they break when you remove these initial tokens? To answer that question, the authors look at attention maps, which are just going to be, I think these are going to be the not the probability, not the weights, but the actual scores before the softmax. So they just plot those, and you have your square attention matrix, right? And what you see is that as you get like fairly quickly into the model, you get this this interesting band of red, right? So there's a lot of attention there. And essentially removing that, just like popping that out of the cache, is really, really removing a big chunk of that attention score. And so if you think of the softmax equation, if I can copy it. Whoops, sorry. Let's try that again. There we go. If you're just popping that out of the cache, you're essentially removing this part of the softmax, and sorry, removing this chunk within the softmax equation, and you're causing the distribution of the outputs to shift a lot, and that's basically messing. So the hypothesis is that this is messing with the model because it's not used to seeing this kind of distribution, and as a result, it starts predicting. It kind of goes into this garbage prediction mode. So. And I think this also explains potentially why the recomputation approach works, is you're not just evicting things, right? You're actually evicting and then recomputing, so you bring the distributions back to what the model would expect. Okay, so, all right, weird that there's this band, and okay, like we remove it, we mess with the softmax, just like output distribution of the outputs. Sounds okay. But why are they so important, right? What's the big deal with them? Why is it initial tokens? And to answer that question, what the authors propose is they say, all right, well, there's two possible options. Maybe those tokens carry important semantic meaning, right? How can you test for this? Well, you just replace them with just new line characters and see how that affects perplexity. And what they actually show that if you just replace these tokens with new line characters, but still keep them as attention sinks, right? So you don't evict them from the cache, you get back a lot of the perplexity you would if you just used the original tokens in this attention sink within the cache. Sorry, as attention sinks within the cache. So seems like it's not about their like they're not carrying any important semantic meaning. And the explanation they propose is that, okay, this model might be learning a bias towards their absolute positions. And why would the model why would the model even do that, right? Why would it learn something like this? And there's a very interesting blog post about this that's called "Attention is Off by One" by Evan Miller that I really, really liked reading. So I would recommend to read it. I think it clears a lot of this up as well. So, if some of these things don't make sense, I think this is great. But basically, if you think about the softmax and you think about the nature of the softmax, you can't have all entries be zero, right? Something has to be picked. There has to be a choice. And the hypothesis the authors propose is that because a single head might actually have sufficient information, it doesn't need inputs from other heads. And in fact, they might not have anything relevant to say. So in some sense, it's that every attention head gets a voice, even when maybe like it can't choose to stay silent, right? And they describe this kind of what sort of happens is you get this extra attention, because remember, you have multiple heads, you're going to aggregate their results somehow. So you get this extra or redundant attention, and it needs to go somewhere because the model doesn't really need it to make inference. So the model essentially learns to just place it somewhere, and it places it in these initial tokens because they're going to be available to, they're going to be visible to all future tokens. So that's their hypothesis for why the model kind of just dumps all that extra attention in those first tokens. Okay, so maybe, right? That sounds reasonable, but why would it use multiple tokens? Why not one, right? Why not just one token is always there? Why not just toss everything in there? And the authors have an explanation for that too. And the way they explain this, and actually, sorry, so I should maybe track back a bit and say what they show is that 4 tokens produces kind of very good results, but 1 or 2 sync tokens is not sufficient. So if you look at this table here,
Is there a diagram? I think you might have showed it earlier, but are they basically pre-pending these tokens during runtime?
Yeah, so if you look at this, so what's happening is you have your KV cache, right? And you're populating the cache, populating the cache, populating the cache. And then once your cache fills up, instead of evicting, let's say token 0, you say, no, this is a sync token, I'm going to keep it there. And the same for token 1, 2, and 3. So instead, I'm going to evict token 4, right? So I'm always going to keep those 0, 1, 2, 3. I'm not recomputing them, I'm just keeping them as is, right? So
nice. So you're literally, if the sentence was like, I went to you're just leaving those tokens in 0, 1, 2, and 3 throughout the entire context.
Yeah, so you're keeping that in the cache. Yeah.
Cool.
And yeah, so they show that 1 or 2 tokens in this cache. Keeping only 1 or 2 is not sufficient. Keeping more is not strictly necessary, but 1 or 2 is insufficient. And they show that 4 is kind of where you recover the vast majority of your perplexity. And they hypothesize that this is because models might not have a consistent starting token. And as a result, the model sort of gets to see random tokens as these initial tokens. So it's sort of, instead of learning that single token as the attention sink, because it sees random tokens as starting the sequences, it sort of learns to distribute that over the first several tokens. And they talk about this in the example with Llama 2, where every paragraph is prefixed with this start special token, but it's done before chunking. So then when you actually chunk the sequences, you have sequences that don't have that special S token in the front. I didn't verify this, but I trust that they're they're not misleading us here. But they do show results that actually I think support this. And the way they kind of validate this is they train a model with a dedicated sync token. So literally just prepend a special token always. Every sequence always gets like a token at the start. It's the same token. And what you observe in that case is that when you do that, when you train with that dedicated start token always there, you actually only need 1 sync token in the cache. You no longer need 4. So you recover this perplexity that you would get with 4 tokens in the vanilla case, which is this without pre-training with a sync token. You get the same perplexity back with a single token when you do the pre-training with a dedicated sync token. And this is literally just prepending us, like making sure there's a special token there always in every sequence that the model can essentially learn to dump attention into.
And this is in addition to the start token.
I think it can be the start token. I don't think it has to be. Sorry, I don't think it has to be an addition. My understanding is that as long as there's a consistent start token always, that's sufficient. Though it seems like they use a separate token for the purposes of they just add an extra token.
Cool.
But I think it sounds like it can be it can be the start token as long as it's there always. And yeah, you can see the results, right? So without the sync token pre-training, you have the attention, this band doesn't, it forms later on into the layers. And in the layer 2, you see it's a little bit more distributed across the first few tokens. Whereas with the pre-training with a sync token, just boom, right? You have this band forming at very early on in the model.
And it looks like it more evenly attends to the rest of the tokens as well.
Yeah,
So,
yeah.
I
think that was, so I think this kind of adds validity to the idea of this is extra attention the model doesn't need, so it's just tossing it in this band here in the first tokens.
Do we have time for me to ask a question here, or should I wait?
I can just, I think so. Let me just show one thing, which is I think the big, I'm gonna just skip over a few things, but and then I'll ask questions. So I'll just quickly show something. So one of the things the authors write is we talked about infinity tokens, so I feel like I should get that in. It's not quite infinity, so it's slightly misleading. I misled you a little bit, but it's 4 million tokens. So that's a lot. It's 100 books. And just to prove to you that this does work in very long inputs. And what they do is they take this PG19 data set, concatenate it, which is 100 books worth of text for 4 million tokens. And they do causal language modeling on this. So they're predicting the next token. And they show that your log perplexity just, it fluctuates, but it maintains within a certain range. So it's more or less stable. And it just continues this way as you keep going into 4 million tokens. So kind of proving that, if you do this attention sync, if you apply this attention sync method, you can keep perplexity at the baseline level, even as you go far beyond the context window. So that's what I wanted to get in. Go ahead. I think Evan, right? Maybe.
Yeah, so I guess as you were talking, I was kind of wondering if we accidentally kind of reinvented RNNs, and what's happening is that the transformer's putting the RNN state into the first token because it's the only place that it always has. And I'm wondering what you're saying is if we just give it a blank token for it to put state into, or kind of opt out of giving an answer, is it possible that it's not just being used to say for a head to say, oh, I don't have an answer, but it's also just storing state that doesn't belong in any other token. And I'm wondering, like, what I see here is you show that, or the authors show that really only you need one of these tokens, and then like adding another one doesn't really seem to benefit that much. Is my understanding correct?
Yeah, so when you do the pre-training with a sync token, one is sufficient. And they actually have some
Yeah.
results in the paper where they show that if you do two, it doesn't offer any benefit, but yeah.
And I
Yeah,
think
so I'm
there's
wondering, like,
one thing I would want to add there is I was a little confused at first, but they're not using any state per se. They're just adding this is only where the model attends to. And my intuition behind it was there's a lot of, and actually Daniel linked to a really good blog post that was called like off by one, softmax is off by one or something like that. And
I see.
the problem with softmax is for every token that comes in, it has to pick something to attend to. And there's a lot of tokens like spaces or commas or stop words that really don't need to attend to anything. So they're just default going to this first token. And then that makes the, when it's always looking back at the first token and you evict that first token from the cache, then it gets all confused. It's like, wait, the thing that I was relying on this entire time is now gone, because they had no other way, no other place to put their attention. And that's why the perplexity shoots up. So this is really just like a safe place for all of those tokens to look as you're generating, is kind of how I interpreted it. Daniel, is that
Why?
a good explanation?
I don't understand what you just said, Greg. I know you said to, yeah, but why would a comma look at the first token and not just look at itself? Like, wouldn't it just have an attention score high on itself? Or shouldn't it?
It does, but it's for one, as you're training, the first token is always there. So that's like kind of a safe one for everyone to look at. And it is a weird, just kind of thing that they notice is why is even in these diagrams here, why is everything attending to the first one, rather than just itself or the ones nearby? Daniel, do you have any other intuition behind that?
Yeah, I mean, I think that's a great question, especially, I think there does seem to be some similarities. It kind of feels like some kind of state where the model is, but my understanding is that, and I think what Greg was saying, right, is that it feels less like state and more almost like storage, at least based on how the authors explain it and how, like what I gathered from that blog post. So it's more like, it's this attention that it doesn't need, essentially. I don't know if that's correct to say, but that's kind of, they call it extra attention or redundant attention. So this is like, okay, it needs to go
I think
somewhere.
it might be
Yeah.
worth reformulating my understanding is. So from what you've said, it's not that you're updating this, it's just that it gets calculated once as like kind of a stable backup for everything that comes after it. So like you're not actually ever updating the value of this first token, it's just getting cached.
Yeah, yeah. So as far as attention sinks go, you're just, well, once you compute this is cached like you would in a cache. And so they talk about why you don't want to evict this, right? Is because this band has so much, like it has such a high amount of like, attention score, right? I guess attention logits maybe, that if you drop this, right, if you remove it, you're removing this huge part of the softmax denominator, right? And you're shifting the values that you get at the result of the softmax operation by a lot. Like you're drastically changing the distribution, and that basically just messed. Like the model just hasn't been trained to look at, like it's not, that's not what it's used to during training, and so you mess with things. So you just keep these attention sinks as is after you compute them in the cache. Because they hold so much of that attention score.
And part of that is due to the training process as well, right? As like you have the mask, so that during training you can't see the subsequent tokens, and training usually happens with a fixed context length during training, so you don't run out of GPU memory.
Yeah.
So once it gets beyond that, it starts to just be like, I don't know what I'm doing.
I think it's worth noting, and kind of going back to what you said of it, I don't have an answer as far as are we reinventing RNNs, because I'm not sure how, like, again, it sort of feels like it's being approached as more of a storage rather than state. But they do talk about this showing up in other places. So like I think in the Vision Transformer, they mentioned that this shows up, and they talk about, I haven't read the Vision Transformer paper, or I've read what I remember there was like the VIT and the Vision Transformer. I don't remember which one is which, but they talk about registers, and it seems like this is a very similar idea. And they acknowledge this in the paper, but they kind of explain the differences as well. And the other thing is they show that this shows up across, this is for decoder only LLMs, right? Or decoder only transformers, but they show that it shows up in encoder architectures too. So there does it does feel like we're finding something out that maybe kind of was there before, but I'm not sure how it connects. Yeah, I can't really answer much. I can't say how this connects to, if this is similar to how things work in RNNs. Yeah.
Yeah, I see what you're saying. I don't think it's storing state. I know that that's not what's happening now. My next question is, like, would this always be the same, like, regardless of what you put in? Because it's always going to be the same start token.
Do you mean like what would be different? Sorry, regardless of what? Could
So,
you?
like, basically you put in tokens and then you cache their, like, generated keys and values. But for the start token, like, you would always know kind of what that first, like, you would know what the key and the value would be for that always. Like, you wouldn't have to pre-compute it because it's going to be in every single one of your prompts.
Yeah, I think I see what you mean. So yeah, so oh, so you're saying if you have the dedicated sync token, you can just have that pre-computed. Is that what you're saying?
Yeah, pretty much. Like, it almost seems like you can, like, why even put it in as a token? Like, if it's always just going to be the same. Like, if it's just going to be part of the model at this point.
It's a good question. I would imagine that it just right, like computing that one like that, computing that the kind of the embeddings for that one token is not computationally expensive, and it's just easier within the existing architecture. So maybe that's why.
Yeah,
I
I
feel
think
like
the
I
reason
think
I'm
there's
thinking of it
a split
is,
between like the doing it during training and doing it just during inference. And if you have the dedicated sync token during training, then it seems like it can update that embedding for the sync token to like be sync token like, versus if you're just doing it during inference time, they
makes sense.
require 4 sync tokens to
I think
really
Alex
get the
brought up
benefit.
he brought up a really, really good point. Um, it seems like we're essentially adding a new type of tunable parameter. Like, we're basically adding a bias parameter to the attention mechanism so like maybe attention was just missing like a way to add this type of bias.
Mm,
Like, maybe we're kind of like, yeah, maybe there's a
that's an
way to
interesting
like,
analogy. Yeah.
yeah, maybe there's like a way, like maybe there's some part of attention that we're missing that causes this to be the solution. Because this seems like really kind of like almost like dumb in a way that this works like this.
Yeah, it does
Like,
feel
it doesn't
hacky.
make sense.
I
Like,
really I do recommend, so like really recommend reading that that post, because I think so. What you mentioned, right, is that like the limitation, like there's something feels like doing like something's wrong. That's kind of what they talk about in the post. In the so yeah, but
The off by one
yeah,
post,
yeah,
right? Yeah, I'll put that in the
because
chat here.
I think it's I think that would be, yeah, yeah, basically I think it's relevant to the conversation. So
It's also a very fun read. It's the guy
yeah.
the guy's just very I love his tone while he's
Oh no,
explaining
I
the
sorry, I
softmax
didn't,
stuff.
Evan, I didn't mean like, oh, all your answers are there. I mean more like you're asking great stuff, and I think that I unfortunately can't answer it well, but I think that this post really kind of helps provide some more information that you might find very useful. So yeah.
Eric, did you have some questions?
Yeah. So I had a few questions. Can you hear me?
Yeah.
Okay, so the first one was that, is this really about like a problem in softmax then? Like, if we could find a different like mathematical like operation to softmax, that like would it be possible to get rid of this problem and not need attention sinks at all in the first place?
Yeah, that's totally what this article dives into. And
Yeah.
he yeah.
Okay.
This is the modification you might be interested, like that's what they talk, that's precisely what they talk about here.
Do they propose an actual algorithm, or do they
No.
just speculate?
Yeah, so they just proposed modifying the softmax with this one plus. And in the paper,
Has anyone tried it?
Great question. I did not look into this because I think they, the author of this post said that if anyone wanted to try it, they're to reach out to them. I think this post is from 2023. I don't know how old exactly, but so I don't know. The answer is I don't know. In the paper, they do talk about it. They do use this zero sync, which they say is the same thing. I won't explain exactly how the same, but they explain in the paper that this is basically this attention is off by 1, because if you have like a perfectly zero embedding, when you take e to the 0, you get this 1. That's kind of how they're connected. But as you see, right, I don't know that just a zero sync, just a zero sync doesn't seem to work. So yeah.
So sorry, quick question here. So typically in practice, we also have temperature scaling. So there's an additional hyperparameter in the softmaxes. If I tune that temperature to close to 0, does that bias still matter in terms of the relative magnitude?
I think this is, so these are different. So right, at least when I think of temperature in the softmax, I think of the, like when you're predicting the last token, or sorry, when you're predicting the final kind of like, when you're basically generating the softmax at the very, very end of the transformer. This here is all about the softmax within the attention mechanism. I'm not sure if there's...
Is there a specific head or layer that we should be looking at? Because as you know, as you go deeper and deeper into the transformer before you hit the end, the attention mechanism is operating off of like not the discrete tokens themselves, but like linear combinations of these tokens. So is there a point at which this matters or doesn't matter?
So they show attention sync plots for different layers and different heads, and they sort of show that this is well, I guess they're not showing all layers and all heads, but their plots suggest that this is a occurrence across the board, right? So kind of as you get into layer like 2 of the pre-trained with sync token model, you start seeing this, and you see it across the different heads as well. It's worth noting that they're pre-training a small model, right? So this is 160 or 160 million parameter model. So I don't know how, like they obviously show that this works. These attention syncs work with things like Llama 2 and so on. But as far as the pre-training, they're using a small model. So I don't know how that obviously would change with the bigger model. But yeah, to answer your question, it seems like it's a pattern that they observe across layers and across heads of the attention mechanism.
Okay, thanks.
I have another question.
Yeah.
Is there a reason that you said it only works up to 4 million tokens, or is it just untested after that? Is that just the highest?
That's the highest they went. They didn't test it beyond that.
But it could work at higher, and they didn't really see any performance drop.
So as far as perplexity, right? They show some other things which I kind of had to omit, but yeah. So when it goes to 4 million tokens, you see the perplexity sort of stays within a range. You don't observe this kind of shooting up into crazy perplexities behavior that you saw with other approaches. Yeah, so I think in theory, that's the idea. Is in theory, this could just keep going, and you would.
Okay.
It's a great question, though.
Also,
but yeah.
Yeah. Finally, also, it looked like they had a learnable sync. Does that mean that in the training they were actually like updating that token, with like backprop?
Yeah. So my understanding is that this doesn't have to be like, it's just a token, right? So it can be the actual like text representation can be anything. It's just a token that they prepend to every input to the model. So it gets its own embedding as a result. I don't remember if they do anything with the embedding, but I think it's just that there's a token that always has to be there basically.
Well, they said learnable, which sounds like they're actually like optimizing that token as well.
Yeah. So it's part of training, and it gets updated. Yeah, as far as I could tell. Yeah.
So then a follow-up question to that would be, when they say we tested multiple learnable syncs, are they having multiple syncs that are like different, or is it like 2 copies of the same learnable sync?
That's a good question. I don't know. So they talk about this. This is more in the appendix. But yeah, I don't know exactly. I just know that they did. I don't know if you could see this. Maybe I could, but I can paste it into the Notion. They show that yeah. So I don't know if it's a copy of the same token, maybe, but they do show that kind of, the model is always going to use all the sync tokens you give it, right? So with one sync token is sufficient. With two sync tokens, you need two sync tokens to recover a perplexity.
I
But
see, but it
they're both learnable. I don't know if they're textually like actual representations. There's a difference. Yeah.
Okay, okay. But it looks like just adding one gets you no increase in performance.
No, the model is going to use it's what they suggest here is that if you give it two, it will use all two, and you will need to use two at inference to recover
With no
perplexity.
advantage doing that.
Yeah, so basically, like, why use two if you can use one? I mean, I guess
Right, okay,
two
that makes
tokens
sense.
isn't a big deal, but yeah, that's their point, is that it doesn't seem like adding a new token does anything for you, right? Other than having to use those tokens. Yeah.
All right, thank you.
Great. Awesome questions, Eric. Awesome job, everyone. And Daniel, thank you. We were getting tons of praise in the chat. You did an awesome job. And thank you so much for sharing the load. Everyone, round of applause for Daniel.
Thank you so much, everyone. And yeah, thanks for letting me do this. Really, really excited. So
if anybody else wants to do a deep dive and put theirself on the line and present, feel free to hit me up in the Discord. Happy to share the love here. But again, thank you so much, Daniel.